Okay, welcome back. We're going to we're going to continue here with our study of balance laws. In this segment and the next one or two segments, we're going to focus on an important result. It goes by the name of the Reynolds transport theorem. And when we present it, though it may seem like a purely mathematical result without much application, where the applications are not very obvious, we are going to use it repeatedly in the next few lectures, right? And you'll really see why it's so important. We're talking of the Reynolds transport theorem. Okay. It does not itself lead to another balance law. It is not itself a balance law, but what we will see is that it's fundamentally important in deriving the other balance laws that lie ahead of us. And in fact, even the law of mass balance that we saw in the previous segment can be explained in terms of the Reynolds transport theorem. Okay? All right. So here is what it is about. We have, as always, our basis. And now I am going to say that suppose we have a point x out here in space. And furthermore, that point x is we can think of it as the current position of a material point. Okay? And so around it, I've drawn the current configuration, omega t. The question we want to ask ourselves is the following. So this is what we've started off with here today is a spatial description, right? A spatial configuration. And we want to ask ourselves that suppose we define some spatial field there, okay? So we have some field, I'm going to label it psi. It's spatial, so it's a function of the current position, the spatial position, and time, okay? The way I've written that field psi, you may think it's a scalar, right? Because I haven't given it our usual vector or tensor notation of an underbar. For now, let's assume it is a scalar. We'll see that it actually the results we are going to derive are generalizable. Okay, so I'm going to say that psi parameterized by spatial position and time is a spatially defined field. Okay, it's something. You may think of it to be whatever you like. It could be temperature, it could be maybe the concentration of some chemical species, and so on. We'll see later that it could also be more mechanical concepts, okay, than what I just mentioned. But let's just think about it this way. Okay, it's some field. Let's for now suppose that psi is a scalar. Psi belongs to real numbers. Okay, so formally what we're talking about is that psi, because the arguments are spatial position and time, it is a map from R3, which is the space in which the spatial position lives, because the spatial position is a vector, right? So it's a map from R3 cross R plus because R plus is the domain over which time extends, right? The positive real numbers. Okay, so it's a mapping from R3 cross R plus to R, and this final R that I've written after the mapping symbol is because psi is a scalar, right? It can take on real values. All right, so that's the sort of setting we have. So the question we want to ask ourselves is the following. We say that, all right, we have psi defined as a spatial field, and furthermore, let's suppose that psi has the properties of being some sort of a density. Let's suppose that psi is the sort of field that one can define per unit volume. Okay, so psi is defined per unit volume in omega sub t. Okay, so now you really think about psi as maybe a concentration. Okay, like just to fix ideas. Okay, so example of psi may be a concentration. Okay, all right. So a concentration then be defined as number or mass per unit volume. Okay, just to fix ideas. All right, so what are we talking about doing here? Right. So if psi is defined per unit volume, we can consider the following. Right? We can consider the following integral, okay, which I'm going to write as integral over the current configuration of psi, and we remember that psi is parameterized by x and t. Now, we're integrating over omega sub t, okay? So the volume element in omega sub t, we are going to denote as d sub little v, okay? That's the volume element in omega t. Okay, so really what I've written here is the volume integral over omega t. But now here's the important one of the important points. Is our spatial or current configuration fixed with respect to time? So if we think of the body, right, here it is in its spatial configuration. We have our basis. Is it fixed in time? In general, it isn't, right? Because time evolves, and we are admitting the possibility, and we've already admitted the possibility in our earlier treatment that the body could be here at this instant, there at a different instant, there at a different instant, and so on, right? So the configurations the body occupies at different times can be different, right? And of course, the body could be deforming as it's doing this. This is the sort of thing we want to think about. Okay. As a result, the t that is used as a subscript here is really changing in time, right? It's really changing, it being time. As a result, the integral that we have, while we're integrating away the spatial dependence of psi by integrating over the volume, we're not going to lose the time dependence, okay? So this integral remains a function of time, all right? Okay, so then one can ask ourselves the following question. We can say, all right, if I is a function of time, we can ask ourselves, what is the time derivative of I? Okay, now observe that question, of course, is well posed because I is only a function of time, so there's no question of partial time derivative, and if partial time derivative, what sort of partial time derivative, and all of that, right? Those questions are just moot. right? So this is what we're asking. What is this time derivative? Okay, and that matters because observe that now if you apply this time derivative to the right-hand side, we have to calculate. So that is what is derivative with respect to time of omega sub t psi x comma t d little v. Okay? This is not a straightforward question. It is a question. So it's not a straightforward question simply because what? What is it that makes this question not a straightforward one? It is that the domain of integration is also changing with respect to time. Okay, so let me say that right here. Note that domain of integration is time varying. Okay? All right? That's what makes this calculation challenging. However, there is an important trick that we will use, and it's something that you've used earlier in your study of integrals in calculus in general. It's a very useful trick, and it's made available to us because of the fact that we have a special configuration here, right? We have a reference configuration that we can think of. So even though the body is here in the spatial current configuration, we are going to use this reference configuration to carry out this integral, right, and this time derivative. All right? So in particular, what we're going to do is the following. We are going to change the essentially, we're going to change the domain of integration. Okay, we're going to change the domain of integration. Okay, we're essentially going to affect here a change of variables. Okay? Okay, that's what we're going to do. Change variables to the reference configuration. All right? The way we do this is the following. We say that d dt integral over omega t psi x comma t d little v, which is what we are confronted with, can also be written as d dt. Now, I'm going to write that integral over the reference configuration, but via a change of variables, right? I'm going to say that instead of integrating over omega t, I'm going to integrate over omega naught, remembering that psi x comma t is calculated with little x, not just any old position out there in space, but a position in space that coincides with the position of a material point, right? Okay, so it's not just some point out in space, but it coincides with the position of a material point where that material point is brought to that position in space by the motion. Okay? So we're going to say here little x is not just any old little x, but little x equals phi of capital X comma t. Okay? Now, we need to do something. If we've changed the domain of integration, effectively the limits of integration, we also need to change that elemental factor that we use in integrals, right? The differential, as it's sometimes called. Okay, so that becomes now, we are going to write d little v, right, as j, and remember j is just determinant of the deformation gradient which comes from the motion, right? J d capital V. Okay, and we are going to remember that j is parameterized by capital X and time. Okay. All right. So this is what we're going to do. Now, the reason this is a useful thing to do is that, first of all, that derivative that we need to carry out, and which would have been challenging to do on the left-hand side because the domain of integration itself was changing with respect to time. Okay, that derivative can now be moved inside the integral sign because now, on the right-hand side, the domain of integration is fixed, right? It's the reference configuration. Okay, so what we can now do is to simply write this as integral over omega naught, right? A time derivative. Now, the time derivative that comes about here, remember, is a time derivative with respect to time only, and the way we can make this equivalent is by observing that the reference position capital X is fixed. Okay? So the type of time derivative we want to take here is the following. We may think of this as a partial time derivative, but it's not just any old partial time derivative. It's not the conventional partial time derivative, but it is the partial time derivative, okay, where little x is obtained from the motion, right, of a material point where now that reference position of the material point is fixed. Okay, this is what we mean by taking this derivative. Okay, and then of course here we also have j. We recall j is properly parameterized by the reference position and time, so there is no ambiguity. Okay, so the derivative that we need to compute is this. Okay, the differential of course is over the reference configuration, and that is fixed. Okay, so this is what we want to compute. Okay. Now, if you compare what we have in the sort of time derivative we are going to take on the right-hand side of this object in the big parentheses, right? The parentheses which start here and end there, right? What you observe is that this is actually in exactly the same form as the derivative we computed yesterday, not yesterday, but in the previous segment, for the mass density. Okay? All right? So, this thing is in fact the following. Integral over omega naught, derivative with respect to time of psi little x comma time, where again we remember little x is phi of capital X comma time. Okay, so we're taking this derivative times j x comma time plus psi x comma time partial derivative with respect to time of j x comma time. Okay, all of this integrated over d capital V. All right?